This week, we're continuing our language levels tour downward one more time to machine language. We do so with three motivations in mind. Now we've seen assembly language, which we know has a direct correspondence to the instructions run by the processor, but we're still left a bit in the dark as to how that works. So learning about machine language can connect the dots from assembly language, which is still human readable, to the actual bits that the hardware sees and interprets as instructions. Number 2, your next assignment requires that you write some machine language of your own. Not necessarily a lot, and with a fair bit of scaffolding, but you have to know enough about ARM instructions in machine language to make use of that scaffolding to build yourself a miniature version of an assembler. And finally, we get to remove one more lie. Okay, maybe not a lie, more like a convenient oversimplification, as we dive into exactly what the assembler and linker do at the bit level. So first we'll talk about machine code at a very high level, and remind you of some things we've seen thus far. Then we'll give an example of how just a little bit of insight into computer security ramifications of sloppily written code, and then we'll get into ARM specifics. We've seen that high-level languages can be largely portable. I want this to just be a reminder that at the lower levels, though, they aren't portable at all. We saw this with assembly language, but this is at least as much and perhaps even more so at the machine code level. So all of the things that we're going to be writing with machine code are very specific to the ARM processor. The general ideas, though, tend to translate. Recall the 4-stage build process we've seen all course. Initially, we have the preprocessor that brings in declarations from a header file, it fills in macro replacements, and throwback to assignment 1, it decomments. Then there's the compiler, which translates from C into assembly. We've done this a little bit by hand, but there's obviously a lot more to it. That's really all we're going to say about those two stages. If you're interested, COS217 is a COS departmental that allows you to build a compiler of your own and deal with all the gory details here. In this course, though, we do still have some material to cover about the assembling and linking phases. The assembler does translation from assembly language into machine language, and the linker resolves all the unfulfilled references within the program and brings in external code from libraries and pieces everything together for the final executable. Today we'll talk about just that first translation of simple instructions into machine language, and next time we'll talk about how the assembler prepares for the linker to do its job, and then the linker's role itself. Before we dig in, though, I want to look through a few C programs that have some interesting characteristics, namely sloppy code that is susceptible to a common mode of attack, eventually leading to one final such program that will constitute the heart of Assignment 5. Take a moment to consider the program on the slide. Nothing seems particularly unusual. There's some bad style, perhaps. For example, we know that getChar returns an int, not a character. But it's pretty typical. We have variable declarations for a name buffer, and a character, and an int counter, and a magic number. We have a prompt to instruct the user to enter their name, reading the name one character at a time until a new line. We then terminate the name with a null byte, and print it out along with another message using the magic number. When we run it, it looks great. At least for John Smith. For me, not so much. 12 characters just isn't going to cut it for a buffer for my name. But hey, the program asks me to enter my name, so I will. And rather than see some sort of nice message that says your name is too long, or even crashing with an array index out of bounds message, we get, well, that. That's not the magic number I was anticipating. So why? How? Well, these were all local variables. We know where local variables go. They go on the stack. In fact, they were put on the stack almost in order from the C. The name, then C, then magic and I flipped. So the actual stack goes like this. Name at offset 8, then 3 bytes of padding, bringing us to offset 17 hex for C. C is only a single byte, So it's offset 1.8 for magic and offset 1c for I. So let's think back to when I put in my name. My name used all 12 bytes of name, plus the 3 bytes of padding, plus the byte for C. But that byte kept getting overwritten each time we read in. That's why you don't see the E in Moretti on the previous slide, since that's the 16th character in my name, including the space. But in that location was the new line, which was the last character put in before the loop broke. When we read in the first T in Moretti, we overwrite the 42 with T, which is hex 74, because the 42 is actually stored in the first byte of the int. The 3 high-order bits remain 0. Recall this is the discussion we had earlier in the term about little endian versus big endian architectures. The next T makes magic hex 74 hex 74, that's 29,812, but the 2 higher order bits remain 0. Finally, the I makes magic hex 69 hex 74 hex 74, which is that 6911092 number. In this case, now only the first high order bit remains 0. If we keep writing, not only can we blow away magic, we can get out of this function stack frame entirely. And what's at the top of the previous function stack frame in every assembly function we've written thus far? It's the return address it will return to when it's done. So if we keep writing, we can change the function that called us to return someplace different than it's supposed to. If we put a garbage value there, that program will segfault. In this program, we'll return from main to underscore start, and underscore start will return a garbage location. No big deal, the program was over anyway. But imagine instead of doing this in main, we do this in some other function. Now we can cause it to crash in the middle of the program. But that's just getting started. Instead of a garbage location, what about a specially targeted location? Say somewhere in text that you weren't supposed to be able to get to on this logical path, or somewhere in BSS that you've copied malicious code into via another attack. This could be a disaster. You have completely hijacked the program, all because they didn't check to make sure that they would not write beyond the buffer. I'd love to tell you that there's good news here, and there is. It's actually really easy to avoid buffer overflow attacks. The bad news in this class is the key way to do that is not write in C, which isn't really an option here. So failing that, the manual pages all note that stir copy isn't great and you should use stern copy instead, and gets isn't great and you should use fgets instead. And there's a lot of other good code techniques that we should follow that would avoid these. Further, modern operating systems have some additional security rules. For example, you can only execute code from within the text section, or the stack section starts at a different location each time the program runs. Naturally then, we come to assignment 5, where we turn off these protections. In this program, which has been specially arranged to reduce its shields and turn off these defenses just mentioned, we have a main program, a main function, that calls another function to get a name, and that name is stored in the BSS section. Main then compares the name that was read in with that of Professor Appel. If it is indeed Andrew Appel, he gets a B, and they say grade deflation is dead. Otherwise, anybody else gets the grade unmodified from the default value of D. Your goal in assignment 5 is to get yourself a B, an A, or even an A+. So let's see what's in that elided out portion, which must contain the definition of getName. GetName simply writes the prompt, then calls readString. No problem here. ReadString, though, declares this buffer of the same size as the one in BSS. It reads in the name into the local buffer until either a new line is read or there's the end of input. Note, it doesn't check whether we're still in bounds of the buffer. After reading everything into the local buffer, it fills up the buffer in the BSS from its local buffer. So your job is to execute 3 different stack smashes to earn yourself a B, an A, or an A+. In the B attack, you'll overfill the buffer in read string with null bytes to get far enough down to write out of read string stack and overwrite the return value, the return location, that is the stored value of x30, on getNamed stack. Now you'll return from read string as normal back into getName, and getName will return, but not as normal. Instead, it will go to the spot in main where we set B to be the grade for Professor Appel. So now instead, you'll set your grade to B and finish out the program as normal. That's the B attack. In the A attack, you'll overfill the buffer in read string to get far enough down to write out of read string stack and overwrite the return address to get to on getName stack. Exactly the same, except instead of returning from getName to another spot in the text section, you'll go to the BSS section, where all the stuff from your buffer has been copied. And what's in that buffer? Not null bytes like before, but instead instructions for you to execute so that the program will do your bidding. Like, say, setting your grade to an A and then jumping back to the text section to print it. But these instructions can't be C code. That's not what gets executed. They'd have to be compiled. And they also can't be assembly code, because that's not what gets executed either. They'd have to be assembled. The instructions injected into the BSS section, if they are going to be executed after returning to getName's corrupted return address, must be ready to execute immediately. Thus, they must be machine code. And this is why we're going to talk about ARM machine language for the rest of this lecture. So now let's turn to the details of ARM machine code. We know what the assembly instructions look like. We can now read them in English, just at a glance. Add x1, x2, x3 is add the contents of the 64-bit registers x2 and x3 and store the result in x1. And here's what the corresponding machine instruction looks like. It's not at all apparent what parts of that are which. It's not at all human readable. But it clearly must still contain an encoding of the verb and each of the nouns. But even with intense inspection, without substantial documentation, we can't make much of it. We could try and guess, like, hey, I see a 1 at the very end, maybe that's corresponding to x1. As it ends up, that's right, but it was nothing more than a lucky guess. So we'll need to learn about the overall structure of machine language instructions, and then additionally the specifics of each individual one that we're concerned with, that we'll need for our A attack. Let's start off with the former. What pieces are part of a machine language instruction? Let's again think back to toy. All instructions were the same size, 4 hex digits, which is 16 bits. But we had multiple different formats for instructions. Each one had an opcode, which indicated what the operation was. Think of this as the verb. Some had 2 source registers and a destination register. Some nouns. What were the verbs acting on? Others had addresses or immediate value and a destination register. Again, the nouns. ARM is going to be similar in some respects. All instructions are 32 bits long. There are a variety of different instruction formats. All instructions are stored in places in memory that have addresses as a multiple of 4 for reasons that we'll see later and hardware simplicity. Each will have an opcode, and then bits identifying the registers, the memory offsets, the immediate values, etc. So the rest of this lecture is going to fly through a whole bunch of examples of these, but you'll definitely want to look back at these slides in much more detail as a reference when completing Assignment 5. Since all ARM instructions are 32 bits, we can be consistent with identifying the bits. We'll start on the least significant bit and index from 0. So over there on the right side of the slide is bit 0, while the most significant bit on the left side of the slide is bit 31. Before we start our breakdown of the instruction, we need one more vocabulary term, operation group. This is a grouping of opcodes that all share a common bond. For instance, 3 register data processing instructions, or branch instructions. The operation group is encoded in bits 25 through 28, but as you can see indicated by X on this slide, it doesn't necessarily use each of these bits for every operation group identifier. When those bits are not used for the opgroup identifier, they are typically repurposed, often for the detailed opcode. We'll take each of these operation groups in turn, seeing one or more examples of each that might be relevant to Assignment 5. Our first opgroup will be data processing instructions with 3 registers, 2 source, 1 destination. We'll need the verb, the opcode. That's an extension beyond the operation group, 1 to the right, bit 24, and additionally bit 30. These are all in burgundy. We'll need 3 nouns, the first source register, the green bits, the second source register, the orange bits, and the destination register, the blue bits. Note that each of these registers is allocated 5 bits as an identifier. This is the perfect amount to uniquely identify 32 registers, 0 through 31. Conveniently, we have 31 registered numbered, 0 through 30, encoded as their own number in binary. We'll also sometimes use the 0 register, XZR or WZR, or the stack pointer, SP. When we use either of those in our instructions, they would be encoded as 31. We'll also need to specify whether these registers are W or X registers. That's bit 31. The most significant bit over there on the left side of the slide, in pink. And we'll specify whether the option should modify p-states condition flags. That's bit 29 in cyan. Let's look at a concrete example, the add instruction from the motivation slide 3 slides ago. So our verb now is explicitly add, not just some operation that does data processing on 2 registers and puts the result in a third. That means we're able to fill in bits 24 and 28 and 30, in addition to the operation group. So those are still the burgundy bits. Our nouns are explicit now too. The green bits, 00010. That's the number 2 in binary, representing register 2 as the first source. The orange bits, 00011, that's 3, so register 3 is the second source. The blue bits, 00001, that's 1, so register 1 is the destination. The pink bit at the far left is a 1, indicating these are X2, X3, and X1, not W2, W3, and W1. And this is add, not add S, so the cyan bit 29 is 0. That's all the information we need. The remaining bits are 0. Take some time to pause the slide here and see how we can break the 32 bits down into separate fields for each to be filled in to encode a piece of information that we know about the assembly instruction, but need to put somewhere into the machine code instruction. If you don't get this example, look back over it again until you do, because the others will build on these same ideas, and so it would be foolhardy to rush into them without a really solid grounding. Okay, so our second op group will be data processing that has a destination register, and then either a source register and an immediate, or just an immediate value. The 2 varieties will have 2 very slightly different formats to fit their requirements. The opcode, again in burgundy, spreads out beyond the core op group bits. The most significant bit in pink, over on the left side, indicates whether we're dealing with W's or X's. So this is the same. Again, the cyan bit 29 still there to distinguish whether we're setting condition flags or not. The destination is still the 5 least significant bits. This will be a recurring theme. Most operations will try to share a similar structure like this in order to simplify hardware. But now, whereas 5 bits were enough to indicate all of our registers of note, we need a lot more bits to indicate an immediate value of any decent size. Here we'll use 12 to 16 bits for the immediate value, giving us a much more considerable range, though frankly still not that big. 2 to the 10 is only 1024, and 2 to the 20 is a bit over a million, so we're not talking about particularly large numbers here. Again, let's look at an example, this time one for each of the 2 variants. Our verb is now explicitly subs, not just some operation that does data processing on a register and an immediate. That means we're able to fill in bits 24 and 28 and 30 in addition to the operation group. And our nouns, again, are explicit too. In this first variant, we have a source register. We look at the green bits, 00010. That's number 2 in binary, so it's representing register 2 as the first source. The orange bits now can be interpreted in binary. When we do, we see a 1 in the places for 2, 8, and 32, so this is 42 decimal. The blue bits, 00001, register 1 is the destination. The pink bit at the far left is a 0, so that means that this is W2 and W1, not their longer X versions. And this is subs, not just sub, so the cyan bit is 1. Now we've reached all the information we need to do subs W2, 42 into W1. Here's the second version of the data processing with an immediate, this time with only an immediate source and a destination register. Here we have a few more bits dedicated to the opcode. Even with a reduced instruction set, there's still quite a few different operations we have to specify. But beyond the verb, we only have 2 nouns, the immediate and the register. The register, the blue bits, 00001, that's 1, so register 1 is the destination. We still need to specify whether that's a W or an X register, so the pink most significant bit is a 1 for X. But let's look at what's new. The orange bits, interpreted in binary, have expanded. There's a lot more leading zeros, so they could represent a much bigger immediate if we wanted them to. But in this case, we still only have the 2, 8, and 32 places turned on, so it's still just 42. Next, we'll move on to some more complicated cases that aren't as easy to interpret. So again, stop the slide here, make sure that you're understanding how to parse our panoply of colors and lots of nitpicky detail interspersed with tons of ones and zeros. Thus far, our constant values, in this case an immediate operand, have been absolute values. We saw 42 and that meant 42. But consider that some literal values might be too big. For instance, how could we possibly put an arbitrary 64-bit address inside a 32-bit instruction? We can't. Thus we have to work around this in several clever ways. Some instructions will use relative values instead. 2 different instructions in the text section are likely to be a relatively small number of bytes apart, certainly not far enough to need 64 bits to address. Addresses and numbers that are well aligned, recall this means a multiple of some specified power of 2, often 4 or 16, require fewer bits to store if we know this property. To see why, consider in decimal that if I ask you to represent 2,500 as the number of hundreds, you can do this with just 25, because the 2 trailing zeros are implicit. So our next group is branches, which will have an opcode, a relative address, which we know must be 32 bits long and must be 4 bytes aligned, based on what we claimed about all instructions in ARM, and potentially a condition code for conditional branches. We won't store the entire address, because we can't. We'll store only the relative address, the distance from this instruction to the location we're branching to. And that should be smaller. And we won't store the last 2 bits of the relative address, since when we subtract 2 numbers that are both multiples of 4, the result will also be a multiple of 4. Let's look at a few examples. First, the unconditional branch. The only 2 pieces of this instruction are the opcode, in burgundy as usual, and the relative address bits in orange. In this case, the orange bits look gigantic, but we'll interpret them as 2's complement because these are a signed number. We could be jumping forward or backward. In this case, we interpret it as 2's complement. We look at the leftmost bit. We say that that's a 1. Here I mean the leftmost of the orange bits. So we flip all the bits and add 1. That turns the 24 leading 1s into leading zeros and a trailing 1, 1. This looks like -3, but it's not. Remember, this is the result of right-shifting the value by 2, throwing away the trailing zeros in our example of how many hundreds. We have to left shift to restore the 2 trailing zeros, and so we end up with 1100, which is 12. And since this came from the 2's complement, to get this value, it was negative, so our relative address is -12. We're jumping backwards in the program. And since each instruction is 4 bytes, -12 bytes means we're jumping back 3 instructions. The BL instruction is very similar. It has a different opcode from just B, because we have to specify the detail about how BL will store the address of the next instruction into X30. Other than that, though, it works identically. All the rest of the bits are the same. The relative address is right-shifted by 2 places. That is, in fact, all of the rest of the bits. The last example of branch instructions is a conditional branch. Here, recall that we have fewer bits for the relative address because we have to use some for the condition code. In this case, we have 4 bits for the condition code, so there are 16 conditions we can represent in branches. Though not all of them are ever really used. For example, there's a BNV instruction, which is the mnemonic for branch never. That is a no-op. In this case, 1101 is for LE. The full table is on pages 4 and 5 of this week's second precept handout, taken from C.1.2.4 of the ARM Architecture Reference Manual. We have 19 bits for the relative address, which works identically to how we've seen the relative addresses in the previous slides. Note in this example, we're branching 3 instructions later rather than 3 instructions earlier, for demonstration and for variety. So we don't have to do the 2's complement conversion. Our leftmost bit in the orange is a 0. We do, though, still have to shift by 2 bits because the addresses were multiples of 4, and thus we shaved off those 2 trailing zeros to make better use of the limited bits we have. So we do a left shift in our computation to turn the 11 into 1100. The penultimate operation group we will consider are memory operations, loading and storing. Here, though we're dealing with memory, recall that our operations use registers and dereference them, so we won't have to store an actual memory address in the instruction. We do, though, have to consider our more complicated memory addressing modes. We'll see 2 here, register immediate offset and register register offset, where the value of the offset is stored in some third register. And we'll see in passing that there will be bits in black for additional information, and that's where we would indicate scaled register offset addressing mode if we were doing it. We also have a more complicated source and destination metadata than just X or W. We have to differentiate loading and storing a byte, a short, an int, or a long. So let's look at 3 variants. One with register offset, one with immediate offset, and one with storing only a byte. That last one should perk up your ears as you think about trying to write the A grade into the spot where D initially resides in the grader program. At this point, you're pros at deciphering these. We have 2 pink bits in the most significant bits, not just 1. In this case, both are 1, so we're dealing with X registers, fully doing 64 bits. We have the opcode for load using register offset addressing mode. The first source register is in green. That's the actual source register, here indicating X1. The second source register in orange is the offset register, here indicating X2. And the destination register, as typically has been the case, is in the least significant 5 bits, marked in blue, here indicating X0. Again, we won't talk about the black bits here, but they are a code that will tell us, we can interpret them as there is no scaled offset here, there is no LSL. For the immediate offset instead of the register offset, there's not a whole lot different at first glance. Again, there's 2 pink bits to indicate the size, byte short, int or long. Again, the burgundy opcode. Though ARM does choose a slightly shorter opcode here, gaining an extra bit for the offset versus before when we knew it would always just be 5-bit register names. Here we want to maximize the possible size. For hardware consistency, we're still going to use the least significant bits for the first operand in blue. But because this is a store, the semantics are flipped, and this isn't the destination, it's in fact the source. A little tricky here. The green bits, likewise, typically would be a source register, here are actually the destination. Note that whereas before we said that 31 could be either XZR or SP, XZR's 0 value isn't typically going to be a useful memory location to offset from. So in these memory operations, we're going to have 31 represent SP. And that leaves the rest of the bits for the offset value. Note here that because the pink bits were 1, 1, we're dealing with longs. So we know the address should be a multiple of 8 for good architectural alignment, and thus we can assume the address will have 3 trailing zeros. We save some bits in the offset by right-shifting the offset by 3 before putting it into the instruction. And that means if it's stored right-shifted by 3, to interpret it we have to left-shift by 3 to restore the 3 trailing zeros. We interpret that 1, 1 value then as 1, 1, 0, 0, 0, or 24. Now let's compare the str we just saw with strb. The bit allocations, colors, if you will, are all identical. The opcode, in fact, is identical too. It's still a register plus offset store. And the register values are the same, storing from register 0 and storing into an offset from SP 31. What has changed, though, is the 2 pink bits. They're now 0, 0, meaning that a single byte, we saw this on slide 31, introducing the character as 0, 0, or single byte as 0, 0, short as 0, 1, int as 1, 0, and long as 1, 1 for this operator group. Since this is a single byte, we don't necessarily have 8-byte alignment, and thus the offset is not right-shifted into the instruction. So to interpret it, we don't left-shift it back. We interpret it as is to get the 24. That means we have relatively less range of offsets by 1 than we did by 8. The last instruction we'll talk about is ADR. It has the bits 100x, like the operation group for data processing with immediate and register, but it's a special case that's distinct from the others. For an ADR, we might be referencing something much farther away in memory. Unlike with a branch, where we're presumably just jumping within the text section, though not in your A attack, we might have a label in text, ROData, data, or BSS. We'd like to be able to maximize our range. So to get 21 bits for the relative address, but maintain where the destination register is and where the opcode goes, we have to actually split up the bits. The 2 lower order bits are in bits 29 and 30, the mint color. The 19 higher order bits are the orange that go about where they have been, bits 5 through 23. That means we're going to have to do some bit whacking to interpret these instructions. Let's take a look. Let's try to have a small offset to make the numbers easy, but still show what we need to do. Here you're familiar with the opcode and the destination register, but we have to now figure out how to interpret the 2 separate spots that combine to be the offset. The orange bits, the 19 high order bits. The mint bits are the 2 low order bits, so we can just concatenate those mint bits onto the end. Of course, the actual bitwise operations are more involved. It'll involve shifting and ending and oring. Nevertheless, concat 10 onto the end of 1100 and we get 110010, so that's 2 plus 16 plus 32 is 50 bytes relative address. So now you've seen a few instructions that are ready to run. We'll be ready to go even slightly lower next time and see how instructions actually get to this point, so that they can be constructed by the assembler and fixed up by the linker. In this lecture, we've seen a bunch of relative addresses and offsets. But what happens when those addresses aren't known at assemble time? For instance, printf is in some external library that hasn't yet been linked, or they're in a different section of memory and we don't know where the address of that section start is. That's all next time, to finish off your preparation for the A attack. But at this point, you've seen enough to start making your memory map and working on your B attack. Good luck.